Y squared plus Z squared equals 16. So Y squared plus Z squared equals 16 is a cylinder that extends, it's parallel to the x-axis. It's actually, its center of the cylinder is the x-axis, right? This. Okay, thank you. And then there's some plane that's cutting through that. I don't know. I have no idea what the plane is, but I'm just sketching a plane, and so then that's gonna cut maybe something like this, right? Is that illustration clear? So when we parameterize this, we get two variables. So those two variables are going to be describing what? Like in general, what surface are we describing with those two variables? What's that? The cylinder? A disk. Okay, and so what is that disk? What is that disk? Yeah, it's a portion of the plane, right? So when we parameterize this, we get our x, y, and z, it's going to be the parameterization of a plane. It's not the parameterization of a circle or a, it's the plane. That set of points is planar. So when we do x, y, and z, we need to have it be a plane. Then but it's restricted by the cylinder. So then we'll have to add another part, like a condition saying it's only the points that are inside the cylinder. Does that make sense? So in terms of the parameterization itself, it's just the plane. So it's the plane 2x plus 3y plus 4z equals 5. So the question is, what two variables do we want to use to parameterize? Probably y and z, because now the condition that cuts that thing off is the cylinder, which is cylinder y and z. So it might make sense to let sorry. Yeah, so what's going to make sense? So we could choose x and y, we could choose x and z, or y and z. And since that cylinder is y squared plus z squared equals 16, probably what makes the most sense is y and z. And therefore, then our y and z are just themselves. And then x would be what? 5 minus 3y minus 4z over 2. Okay? So it's a planar, the thing that we're parameterizing is a plane. So the parameterization should be planar. Okay? But that's for what? Y squared. So when y squared plus z squared is, does it say inside, strictly inside, less than 16. Now, if you want to go ahead and change that now into polar, you could also do this polar. You could do this with r and theta. So maybe that's version 1. Version 2, you could do r and theta, but it's going to be this. So what is y? Y would be like our cosine theta. Z would be r sine theta, C and S meaning sine and cosine, and then 5 minus 3 all over 2. And now, what's the restriction now? R is less than 4. because that's what it means to be inside that disk of radius 4. So either of those is fine. So I didn't specify, but these would both be good ways to do it. But notice that, again, yes, it's a disk, but the points you're parameterizing are planar. They're on a plane. So it's going to be the plane equation is what's going to determine how you're setting up your x, y, and z components. All right, does that help? Is that good? So those are both, there would be other ways to do it, but these would be the most convenient, kind of the most natural. These would be the most natural choices for that. Okay, any questions? Okay, it's getting good now. We got to we've got to where we're going to do some heavy duty stuff now. So I hope you've retained lots and lots of what we've done, because it's all about 90% of what we've covered so far this semester is important. We are like now in vector calculus. This is the hard stuff, but it's the good stuff. But it depends on, like I said, 90% of what we've done so far this semester. So here we go. So we're going to talk about flux today. We're going to talk about what flux is. Before we talk about flux, we have to talk about orienting a surface. So we talked about orienting a curve, right? And when we said it's like a closed, like a circulation integral on a closed curve, what was the orientation? What do we call positive orientation? Well, counterclockwise if it's a simply connected region, right? So we saw that if there's a hole in it, what happened in that hole? It wasn't counterclockwise. So what's the real orientation?
The circle, the part on the left side?
Yeah, you're gonna walk around on this curve such that your region is to the left. That's positive orientation of a curve. So what does it mean so similarly, now we have a surface, a two-dimensional thing. How do we orient a surface? Okay, so on each point of a surface, there are two directions normal to the surface. That should make sense, right? It's like if you think of a surface, there's like one side and the other side, right? A surface is orientable if one normal at each point can be picked in a continuous way. So the easier way to say that is the surface has two distinct sides. If a surface has two distinct sides, then we call the surface orientable. And then we use n vector to be the direction of orientation. The n vector is like an orthogonal vector. So there's like two choices, right? There's two choices. So if it's like a basic x, y, z is a function of x and y, you can kind of think of like up or down. And so then you pick one of those, and that's your orientation. So let's just see what I'm talking about here. So here, like this one. So you think of this surface. So what this is showing is that n is generally the up direction. That's the orientation of this surface. You could pick it to be generally the down direction, but you just have to pick one and then be consistent when you're working with it. Okay, and then there's two kinds of surfaces. An open surface has a boundary C that separates the two sides. And this is kind of like an open surface here. So this is showing an open surface, like this steel surface. And then you have this boundary C going around it. And that's like the border or the boundary between the top-ish side and the bottom-ish side. Do you see that? So that's C. This thing right here is C. It's the boundary between the two sides. That's an open surface. That's an open surface. So a closed surface, think of a surface that's closed. It has an inside and an outside. So what's an example of a closed surface? Sphere, right? Ellipsoid. Or we could make a closed surface like out of a cylinder and two discs, right? If you took a cylinder and two discs, that would be closed. So here's one. Here's a paraboloid with a disc. And that's a closed surface. Here I'm showing that the positive orientation is outward. You could also have inward orientation. But this is, but typically inside pointing out is positive orientation. So notice that consists of some vectors that are heading straight to the right and some vectors that are heading straight to the left. Some that are upish, some that are downish. But those are all the same orientation, positive orientation of the surface. Okay, so what's a surface that's not orientable? So the easiest example is the Mobius strip. You know what a Mobius strip is? Take a strip of paper, put a half twist in it, and then make a loop out of that. That's non-orientable. Because what happens is, if I start here, and I say, okay, I want my orientation to be this way, kind of coming out of the page. Well, what happens is I do that. Okay, well then that's this side, that's this side, that's this side. Okay, well now that's pointing backwards, and we wrap around. Now that's pointing forwards. And when I get all the way back to my point P, what happens? Now it's going the other way. I never crossed, I stayed on the same side, and I got back to point P, and now I'm just pointing the other way. So it doesn't have an orientation. It's kind of like only has one side, right? You can't say that has two sides. So that's non-orientable. We won't do any calculus on those. So the ones we'll work on are open surfaces, kind of have like one side and a front side and a back side, you could say. And then closed surfaces have like an inside and an outside. Okay, questions on that? So this plays right in like what you worked on over the weekend. So you're gonna parameterize surfaces. You got two variables to parameterize a surface, right, in R3. And then when we start working with that surface, we're gonna pick an orientation. Like what was the example we just did? So the example I just did was the disk, the part of the sphere. That disk, is that an open or closed surface? The one that would the example I did. Open, right? That's an open surface. And so then you say, kind of pointing up and out of the page is positive. And then you work on the problem and you stay consistent. And since that's a plane, all the n vectors are the same. They're the same, pointing in the same direction because it's plane. Any questions on orienting a surface? Okay, so flux. So let's do flux, and we'll start easy, and we'll kind of work our way more complicated. So flux through a flat surface. So the first thing we need to know about, before we got more groundwork to lay here, something called an area vector. So an area vector of a flat oriented surface is a vector capital S. Vector capital S. So vectors consist of two things. Vectors consist of what? Direction and magnitude. So what is the direction and magnitude of an area vector? So the magnitude is the area. And the direction is n, the direction of how you're orienting that surface. So it's orthogonal to the surface. N is orthogonal to the surface. Okay, see, here's a quick example. A 5x3 horizontal surface in R3 oriented upwards. What is the S vector? What would the S vector be? Oriented, it's horizontal in R3, and we're going to orient it upward. What would the S vector be? What'd you say? So I got 0, 0, 15 and 0, 0 square root 15. What would it be? Yeah, it's just the area, right? It's just the area. The area vector is the area of your surface. Yeah. So there's no circle here. Yeah. So it would be 15K. If we had oriented downward, it would have been negative 15K. right? 15 times negative k. But so once you pick the orientation, then it's set. And so this area vector is 15k. All right, we're finally ready to talk about flux. So we got orienting surfaces and we got area vectors. So flux is the rate of flow of some vector field through S. So S stands for the surface, so we've got a surface and a vector field. Two things, right? So you're in a vector field, and you've got a surface in that vector field, and flux is the rate of flow of that vector field through S. So do we want, so is this going to be F dot S or F cross S? If we want the rate of flow, we want what? We want how much of F in as much as the direction of S or as orthogonal to S? It's the rate of flow. So orthogonal to S is in what direction? Orthogonal to S is like in the parallel to the plane. That's what orthogonal to S is. Because S is orthogonal to the plane already.
Yeah.
So do we want as much of F as in the direction of S or is orthogonal to S? In the direction, because we want, when we're talking about flow, the flow is going to be orthogonal to the surface. S is already orthogonal to the surface, so we want as much of F as is in the direction of S. Not orthogonal to, so you're thinking orthogonal, or you're thinking orthogonal to the surface, and you're exactly right. But S is orthogonal to the surface, so it's going to be parallel to S. Right? So we want as much of F as is in the direction of S, which is orthogonal to the surface, so therefore it's dot or cross? Dot product, right? We're going to have dot product. F. So F dot S is flux or flow rate. Okay, so if the flux is greater than 0, the net flow is in the direction of n. So this is where the orientation comes in. If you get a positive flux, then the sum total of flow through S, which could be in different directions, but the overall combined total is going to be in the direction of n. All right, so let's look at this example. So water flows at 3 centimeters per second through a circular pipe with a radius of 2. Here's that. We want to find the flux through an elliptical region with n angled at theta radians to the flow. Okay, so the flow is right through horizontally through the tube, through the pipe. And so then S is some surface that's kind of on an angle there. N is our orientation, right? It's our normal vector to the surface. And it's at an angle theta to the flow. Does the setup make sense? Does the problem make sense? Okay, so we're asking what is the flux of F, or of this flow through S? What's the flux of F through S? Okay, so flux is F dot S. And then what was our other formula for dot product? Or what is dot product, right? The other formula is just basically what is dot product? Dot product is? You do the dot product, what kind of quantity do you get? Scalar. And what's that scalar is? What is that scalar? No, but that's not our concept for dot product, right? What was our concept for dot product? Now you guys are talking about, you're talking about parts of a formula. I'm asking what is dot product? You get a value, and what is that value? No. I mean, yeah, so, yeah, you got part of it, but that's not in essence what it is.
Yeah.
What about the magnitudes? Dot what? Dot product. It's the product of the magnitudes. It's the product of the magnitudes. It's the product of the magnitudes. This is the part that students, they always remember the in is in the same direction thing. But what the number is the product of the magnitudes. Today's your day. You remember it forever. Product of the magnitudes. Yes, in as much as they're in the same direction. But first and foremost, it's a product of the magnitudes. Okay, so that gives us what? So if we want the product of the magnitudes, that's F times S, the magnitudes of those. And then how do we get in as much as in the same direction? That's where the cosine comes in. Product of the magnitudes in as much as they're in the same direction. Yeah, so it's like you are multiplying the two vectors together. Dot product, you're multiplying. What are you multiplying? You're multiplying their magnitudes. But only to the extent that they're in the same direction. Okay, so we need F. What's the magnitude of F? Yeah, so it's constant, right? This is easy because it's just this constant 3 centimeters per second. So it's just this constant flow field of 3. All right, now we got to get the magnitude of S. So the magnitude of S is what in this situation? What does it stand for? Area of this thing, right? It's the area of this thing. So we're going to do a little right triangle trick. We know what the area of this is, right? So let me draw that again over here. We know the area of that. And then up here is, so isn't this angle up here in this triangle, isn't this theta? Right there. So we're going to use triangle trig, but instead of on side lengths, we're going to use it on areas, right? So what is the area of this, that's easy, orthogonal to the flow?
4 pi.
And how'd you get that? Yeah, pi r squared. That's the area, that's going to be 4 pi. Did I lose you? Go ahead and ask. It's okay.
Well, I was just thinking, like, I was asking if it was pi r squared or 2 pi r, but I didn't really clarify that.
Yeah, it's just area, right? Area is pi r squared. So we're gonna do like a right triangle of areas, like this vertical and this slanted, and so that's going to be pi r squared is 4 pi. And then how will we get the blue one? What's the relationship of theta, the blue area, and the red area now, thinking about triangles?
Cosine.
Right, cosine theta equals?
Red went over.
Right, it's going to be 4 pi over the magnitude of S. Everyone see that? Cosine is going to be adjacent over hypotenuse. So that makes our our S vector is 4 pi over cosine theta times cosine theta, which shows you what? That the angle doesn't matter, right? The cosine thetas are going to go away, which means it doesn't matter how you angle that thing, you're going to get the same flux through it. And the flux is 12 pi, and that's going to be centimeter cubed per second, because it's a flow rate. It's a flow rate. Any questions on this very easy starting example, just to get the idea of flux?
So will theta ever matter, or is it just in this problem that theta cancels out?
Yeah, just theta is the angle of inclination of the plane. So yeah, so with a greater theta, you get a greater area, but then you have less to the extent to which the vectors flow through is less, right?
Yeah.
Right. So if you're a really shallow angle, you're much less orthogonal to the flow. If you have a really small angle, then you have close to being highly orthogonal. But just for this example, the theta is the angle of the plane, and it doesn't matter. Other questions? Okay, starting hard, starting easy, gradually gonna work up to hard. Okay, so here's one. So S is the surface x equals 1, and that's from 0 to 4 for y and 0 to 2 for z, and then here's our field. Right, so these problems involve two things that are independent of each other. So you got this vector field, and then you have this surface, and those are independent things. You can put any surface you want in any vector field you want. Okay, so here's our S is the surface x equals 1, y from 0 to 4, z from 0 to 2, and then the vector field is y minus 1, z 0. It's an R3 vector field. We've had lots of practice with those, right? Given any point in space, those components tell you what the vector is for that point in space, right? All right, so you should be able to sketch that surface very easily. Right? Can you make a sketch of that surface? Here's my sketch. Is that what you got? Don't try to sketch the vector field. That would take too long. I'll just show it here. So this is this surface in this vector field. Okay, x equals 1, y from 0 to 4, z from 0 to 2. Okay. So if we're interested in the flux, which vectors of the vector field are we interested in? Are we interested in all those vectors that I'm showing? Which ones are we interested in? So the ones at the surface, right? We're only interested in the vectors that are associated with the points of the surface. So I can show that like this. So here's a view of all the, or some of the vectors associated with those points of the surface. And then for those points of the surface, for those vectors that are associated with the points of the surface, what are we interested in terms of if we're interested in flux? Okay, the magnitude of them. Are we interested in all aspects of those vectors if we want flux? So what aspect of those vectors are we interested in if we're talking about the flux? Right, so the components of those vectors that are orthogonal to the surface are going to contribute to the flux. The rest of it that's parallel to the surface will not contribute to the flux, right? Flux is because flow right through, right? Flow right through. So I'm showing you an example of the vectors on the surface, but really we're just going to be interested in not in that. Here. We're just interested in the components of those red vectors that are orthogonal. So those are the blue ones. The blue vectors are just the parts of the red vectors orthogonal to the surface. That's all we care about. So if we orient to this surface, we can either orient in the positive x direction or the negative x direction. If we orient it in the positive x direction, do you expect the flux to be positive or negative? Is it positive everywhere? No, there's this part close to what? close to y equals 0 where there's a little bit of negative. But most of the flow is in the positive x direction. So if we orient in the positive x direction, we should get a positive flux. Okay, any questions on understanding the problem here? Let's go back and do it. Where's that? So, what do we need to do this? So what's different about this problem than the previous one? Right, before the vector field was, all the vectors were exactly the same, right? There was just that 3 centimeters per second to the right. Now, as soon as you move around on the surface, your vector changes, right? Your vector in the field changes. So how do we handle that? How are we gonna get the cumulative result of flow if as soon as you move around the surface you have a different vector? It's gonna be, how are we gonna handle that? It should feel like a very familiar problem now that we're in Calc 3. He's suggesting an integral. What do you think? Yeah, we're going to need to accumulate little bits of flux across that surface, right? So a little bit of flux will mean our area vector is not going to be for the whole surface, but what will the area vector be? For like a little tiny element where we can assume that f is held constant. So what is that tiny element? What are the dimensions of a tiny element like that? dy and dz. So it's like our little dA. So like our little element is going to be dy dz, for which we can assume f is constant. And then we can do that over the whole surface, and then we can add up all the little bits of, so we're going to do a little bit of flux through that, and then we're going to add up all the fluxes for all the little points. So rather than f dot s, now it's going to be what? F dot what? So rather than dA, now we have to think in terms of vectors. So it's not just the area, but the area vector. This is going to be f dot what? ds, right? It's going to be a little area vector, right? A little area vector. So this is still an area vector. It's just for a small element. All right, and so what is that? What is ds? So what is f? F is our y minus 1, z, 0. And what is ds, right? What vector is ds? It's an area vector. Remember what we said about area vectors. So what would that be? Zero dy dz. Is that right? What's the direction of the area vector? Positive x. And what's the magnitude? That should be a capital. John, you changing your answer?
Yeah.
So remember, area vectors have, oh, that's really big. Area vectors have direction and magnitude. Direction is in the positive x direction, so orthogonal to the little surface, right? What's the magnitude? The area, right? Area vectors have magnitude, which is the area, and direction, which is the direction of n, orthogonal to the surface. So everyone write down what this area vector is, ds. Should be able to do it, right? Area vectors have. Area is the magnitude is the area. The direction is n, which and we're going to say that's the positive x direction. So what vector has the area as the magnitude of it, and the direction is in this direction? Lane has it. Who else? Jitong, did you get it? What's the area of this thing? dy dz, good. And so now how do we make a vector whose area, whose magnitude is dy dz and is in the positive x direction? If it's in the positive x direction, then what's the y component? And what's the z component? The vector is in the positive x direction. 0. All the direction is in the positive x direction, and the area is dy dz. Therefore, the vector is dy dz, 0, 0, right? Magnitude, dy dz, direction, positive x direction. So what's that? That's like our little bit of flux, right? This is our little bit of flux for a single element. And what are we going to do to get the flux through S then? Integrate it across all of this. What does that mean? If we integrate across all this surface, that means what? Double integral over S of this dot product. And what's that dot product? Y minus 1 times, and that's it, right? Because the rest goes away, because times 0 times 0. Yeah, so the flux through S is going to be the double integral over S of f dot ds. So we got to take a little chunk at a time. So that's our little area vector dotted with f at that little area vector, and then accumulate all of those little bits of flux over the whole surface. And so then how do we, what is that? What's our limits on our double integral? Super easy, right? I got dy first. So y goes from 0 to 4, 0 to 2. Do the math, it's easy. You get 8. It's an easy double integral, you get 8. And what do we expect? Positive or negative? Positive. So that checks out. Okay. Any questions? This is the really easy stuff. So make sure we got the general principle down. Got it? Any questions? Okay. Do you have a question? Oh, okay. Oh, you're saying. Oh, I'm not surprised. All right. So now, flux through any surface. Here's where it gets harder. So not only do we have a varying vector field, but we have like a curve, just a generic any surface, curved surface. Why is that hard? Because then as you move around the surface, n changes. Right? It's always that direction orthogonal to the surface. If you have a flat surface, especially parallel to one of the planes like we just had, super easy because we saw that it was easy. But this is harder now. So we have a parameterized surface, and our two, whatever we're choosing, our two variables are u and v. This is what you worked on over the weekend. And so again, we're gonna we're in a vector field, a varying vector field. So we got to partition this thing up. And we're going to look at one typical element here. So this is one typical element on the surface in our partition. So I call it Sij. And so what we need is for that, we need the n vector for a typical element, right? That's orthogonal to the surface. And where's that going to come from? So we've got this element. An element could be any of those elements that I'm showing on the surface. These could be super small. So where's that n going to come from? Yeah, but how are we going to get it, right? How are we going to get that vector? Of what? Yes. Right, good. So if for that surface, the partial derivatives are going to be in the direction of u and v. They're going to be these if you hold, say, u constant and look at the partial with respect to v, well, that's going to be the direction of, say, this trace going this way. And if you hold v constant and take the partial with respect to u, that's going to be the direction of the trace going the other way. That's the general idea. So the partial derivatives point in the direction of the contours of the surface. And then if we scale those, we're going to scale those down to, say, times delta u and delta v. So delta u is like the change in our partition this way, and delta v is how we're partitioning it this way. So we're going to take those partial derivatives, and we need to scale them down so that these vectors are kind of replicating that element rather than being too long. So if you just take the partial derivatives, they could be way greater in magnitude than the actual edges of your element. So maybe those are the partial derivative vectors in proportion. So we multiply those by the delta u and delta v to scale them back. Okay, so du, ru, and dv, rv are scaled to the size of the blue element. So that you get this little parallelogram, right? This parallelogram, which is trying to be like the curved blue element, right? So this is showing the original element that's on the curved surface. If you take the partials, you're going to form a parallelogram out of those, which is kind of like trying to be that little element of the curved surface. Parallelogram, remember? Yeah.
Is that a comma or a dot? Sorry, I can't see the RU
Comma. So parallelogram. Remember what parallelogram? So what do we need? We need the area of that parallelogram. If we're going to get the area vector, we need the area of that parallelogram. And we need the direction orthogonal to it. Anybody remember? What's that?
Isn't that cross product?
It's exactly what the cross product does. Remember that the magnitude of the cross product was the area of the parallelogram formed by the two vectors. And the direction of the cross product is? Orthogonal. Is perfect, right? It's exactly what we need. Cross product does exactly what we need because it gives us that area in that direction. That's the area vector we need. So what are we going to do? We're going to take the cross product of these scaled partial derivatives. And that will give us that pinkish, reddish area in the direction orthogonal to the surface. So the area of the red parallelogram, which is approximating the blue element, is this. It's du/ru cross dv/rv. And you can pull the du and dv out of the cross product. Those are just scalars, so we can just pull those out. So we get ru cross rv then times du dv. Now notice that's the magnitude. That does not have direction. So this ds is what? Is the magnitude of the area vector, which is what? What's the magnitude of the area vector? Remember? Area, right? So the magnitude of the area vector is the area of your surface. So this D capital S is the area of this red parallelogram. It's just the magnitude. Okay, so as a side note, we're working on flux, but as a side note, if we just found the area of a little element, then we can use that to find the surface area, right? So if we have the area of one little element, how would we find surface area? What's that? Yeah, you're just going to integrate that over the whole surface, and you'd get area of the whole surface. So this is kind of like a side discovery here as we're working on flux. We just came up with ds, which is the area element. And so if we integrate all our area elements, we're going to get area. So this is like an aside. And you have some Weber problems on this, okay? So what are you going to do? You have to parameterize the surface in terms of u and v, like you did for homework. And then what does this tell you to do? Find the partial derivatives. Take the cross product. Take the magnitude of that. And that's going to be that represents the magnitude of one of these elements. You can integrate all those over R. So this is just formula following. Okay, so we know where it comes from. We just derived it. But in terms of doing the problems, you know how to orient this, or you know how to parameterize the surface, and then you just follow this. First partial with respect to u, first partial with respect to v. Those are vectors, vector functions, cross product, magnitude. Okay, now back to flux. So then a point area vector would be that area times, like as the scalar for n, right? So n is a unit vector orthogonal to the surface. So n ds would be our point area vector. So what's n? N is the unitized ru cross rv. That's n right there. Right? Find the cross product and then find the magnitude of it, or divide by the magnitude. That'll be a unit vector orthogonal to the surface, right? That's our n. ds, we just said, was the magnitude of the cross product, du dv. So this all here is our ds, but you see what happens there? Magnitudes go away. So we're left with ru cross rv, the true cross product vector, dA, which is du dv. U and v are whatever variables you chose to parameterize your surface. Remember, sometimes that's x and y, sometimes that's r and theta, sometimes that's y and z. So therefore, the flux is the double integral over S of f dot ds. So that's going to be f dot, so we just found out what ds was. So it's going to be f dot ds right there.